Alright, hi everyone, let's solve another example. This time it is question 11 on page 33. So instead of reading the question, I'm just going to show on the diagram. I think it makes more sense in this case. We are shown a diagram with three charge. Q1, a positive charge with 0.2 microcoulomb. Q2, a negative charge with minus 0.4 microcoulomb, and Q3, a negative charge with minus 0.1 microcoulomb. We are given some distance. So, for instance, the distance between Q1 and Q3 is 3 meters, distance between Q1 and Q2 is 5 meters, and the distance between Q2 and Q3 is 4 meters. We are asked, find the net force acting on the first charge over here. Now, in order to find the net force, it's always a good idea to draw a force diagram. So here we draw our x and y axis. Might as well add the x and y. From the point of view of the first charge, there's two forces acting on it. There's the force Q from the third charge, so the third charge on the first charge, and since the first charge is positive, the third charge is negative, they will attract each other. So from the point of view of the first charge, the Q3 is pulling it downward. Now note, due to Newton's third law, Q3 is also being pulled upward, but we don't care about Q3 here. We care about the net force on Q1 for the moment, all right? So from the point of view of Q1, F13 is pointing downward. It is already a 1D vector pointing in a negative y direction. Now the second vector, so the second force vector will be between the force between Q1 and Q2. And you can see that this one has an angle, and we will need to find that angle. So we draw the force vector over here, and again, it's a positive and negative charge, so they attract each other. So the force will be pointing in that direction. So the angle over here is this angle over here. We are going to need to find it to break the 2D vector into the x and y component. All right? Actually, that's what we're going to do right now. We are given the side of the triangle, and remember that the sine is the ratio between the opposite side and the hypotenuse. Opposite side is 4 meters, hypotenuse is 5 meters. So if we use the inverse function of sine, so inverse function of sine of 4 divided by 5, we get 53.13 degree. It is the angle over here. All right? Now, when we are dealing with 2D vector, I find it more convenient to find their magnitude right away. So the magnitude, and there's no sign here, simply the magnitude, so the absolute value of their distance. So basically the distance of the force vector 1, 2, and the magnitude of the force vector 1, 3. So for the force vector 1, 2, now note, although I'm not going to do the algebra here, we did it plenty in the previous example, I want you to know that the distance between 1 and 2 is 5 meters in this case, okay? So that's really important. It's not written here, I simply wrote the answer to the calculation, but really the radius is 5 meters. That's an important distinction. We get a magnitude for this force vector to be 2.88. multiplied by 10 to the power minus 5 in Newton. Let's find the magnitude for the second force vector, so force vector between the first and third charge. In this case, it is 2 multiplied by 10 to the power minus 5, again in Newton. Now note that the distance here is 3 meters. All right. Now the 4 meter is not really needed in this case. I use it to find angle, but there's other way to find it. All right. But to calculate the magnitude, only the distance between the charge we're considering is important. Now the next part is breaking these vectors into their 1D component. Once they are in 1D component, we can add the x together, we can add the y together, and then recreate our final triangle, which will be our final vector. One thing I want to point is the force vector 1, 2 as a component in the x. It will be pointing that direction in the positive x direction. There's a component in the y. It will be pointing downward in the negative x direction. And for the force vector 1, 3, it is already a 1D vector. It has no x component. It is pointing strictly in the negative x direction, negative y direction, sorry. All right, so let's find the x component of F12. Notice the x component is pointing the positive x. It will be positive, so we multiply the magnitude multiply by sine 53.13. Now the reason we're using sine here is because we can imagine if we were to redraw the two sides of our triangle when it comes to f12, the x component will be on that side over here, opposite to the angle. So if it's opposite to the angle, we need to use sine. So we get 2.3 multiplied by 10 power minus 5 Newton. So we repeat a similar process to find the y component, but now instead of using the sine, we're going to use the cosine. And also an important part is that the x component, so this vector is pointing at the same time the positive x and the negative y. And you need to add a minus over here, all right? So minus 2.88 multiplied by 10 power minus 5 multiplied by cosine of 53.13. And we get minus 1.73 multiplied by 10 power minus 5. All right, now we're going to do the same exact thing for the force vector 1, 3. Now, this one, when it comes to the x component, we have no calculation to do, and actually, we don't have any calculation to do for the y component either, because f13 has to be 0. There's no component in the x. If there's no component in the x, that means the total magnitude is pointing, in this case, in the negative y direction. So basically, f13y is equal to minus the magnitude, and the magnitude is 2 multiplied by 10 power minus 5. All right. Now, I will need more space to finish this problem, so I'm going to erase the top part over here. If you need to write down anything, pause the video, do it now. All right, so I'm looking for the x and y component of the resultant vector, of the net force vector. I'm gonna simply write them as fx. So fx, we need to add the x component, so it's 2.3 multiplied by 10 power minus 5 Newton. And no, there's no x component for the force vector 1, 3. So this is our value. It is pointing in the positive direction. That's an important distinction. So this is positive. Okay, so fy, we need to add the two components. In this case, there's two of them. Both of them are pointing in the negative direction. So it's equal to minus 173 minus 2. Both of them are multiplied by 10 power minus 5. So we get minus 3.73 multiplied by 10 power minus 5 Newton in this case. All right, so again, I need more room to finish the problem. If you need to write down these pieces of information, pause the video now. All right, now a good idea is often to draw back the triangle, just to get a sense of how we can calculate the angle and how we can calculate the magnitude. I like to draw it on an x and y axis diagram. It is more helpful when we want to find with respect to which axis we are considering the angle. So here we got x, y, we got the force in the y direction. It is pointing in the negative y. It is slightly bigger also than the x component. So the x component is pointing in the positive x. So remember, we are adding these vectors, so we link head to tail to the other one, and we draw a resultant vector over here. This will be our net force. Now, no, there's to find the magnitude of the net force, this is we simply need to use the Pythagorean theorem here. So we take these two values and we multiply them. By the way, I made a mistake over here. This is not a 3, this is supposed to be a 7. So let's find the magnitude first. F net, magnitude, it has to be 2.3 multiplied by 10 minus 5 square plus minus 3.73, and all of this is square, and we get a magnitude of, in my calculator, and we get 4.38 multiplied by 10 power minus 5 Newton. That's That's the magnitude of the force. Oh, one thing I want to point out, I'm a French Canadian, so I use the comma instead of the dot often. In the past, it confused some of my students. So if you see the comma, it's the same as the dot in English, okay? Just a distinction over here. Now, I'm going to find the angle over here to indicate the direction. And basically, this side over here is our x component. This side over here is our y component. So the angle can be found using the inverse tangent of fx divided by fy and again, by the way, I'm using the absolute value in this case. And I get an angle of 31.66 degree. Now note, I decided to use this angle with respect to the negative y-axis. If you decide to use that one, that's completely fine also. It's simply 90 minus this value. But just to make sure we get a glimpse of all the different notation we can use. For the angle, we have 31.66 degree to the right of the negative y-axis, to the right of the x negative axis. So the final vector, f net, is equal to 4.38 multiplied by 10 power minus 5 Newton, and with an angle of 31.66. Now note, written in that format, it might not be exactly obvious that with respect to the negative x-axis, actually it's negative y-axis, sorry about that. Negative y-axis, it's not obvious when we look at the value here, so it's important to write it down to make sure it's very as precise as it can be. All right, so we are done with question 11. We actually have only one more example left in chapter 1, and then we are done with chapter 1. So see you in the next example.